Hey everyone, how are we doing? We look to be live here. I hope we're live on the YouTubes. If you're in the chat, feel free to say hi. Mubot will give you some points. With that, we're going to get started here. I think Mubot's awake. He's awake. Who knows if anybody got points? Let's go to live chat on the YouTube. Hey, Angelique, good to see you here. Put those questions you have in the chat. We're going to start up right here doing some BAS 320 activity. So let's just jump into it. So this is the activity number 6 for simple linear regression part 2. And what are we going to use? We are going to use the bulldozer data set. So this is data on bulldozer. Caitlin, good to see you here. We're going to use some bulldozer data set. And with this, we need to first load in reg class. So reg class has in it the bulldozer data set. Now, what is reg class? It stands for regression class. We'll throw out some more points right there since we got people here watching. And this is going to have a bunch of stuff in it. What do I mean? Well, packages, which I have a whole ton loaded in right now, are how we have access to all the different functions and different data sets. Reg class is in here somewhere. I loaded it up a while ago. So you can see here different functions that are inside of reg class. We don't need to go into this much detail right now, but these are the things you've loaded in by doing library reg class. And probably just change back to the global environment now. Notice I have nothing in my global environment, starting off with a clean slate right here, tabula rasa. Now, when I do data, data loads in data that we have access to from all the different packages. Yours probably doesn't say these right here because you don't have the HCharter package. You notice here there's reg class. These are all from different packages right here. And you can see TISBL data, all these different things. But if I type in bulldozer, now we can see the bulldozer data. So once again, this is not like loading in an Excel file. It's like preloaded in games and you bought like a multi-pack. Everything's video games with me. So we load in right here the bulldozer data by going data bulldozer. Now, if you look, it's loaded in. That was not an Excel file on your computer. That was thanks to you to one of the packages you've loaded in. Other packages have other data sets. And if you download that package and install it, you get free data. We like data. So there's the bulldozer data set. We've read it in, 924 observations. What does this look like to anybody? Like if you take a look at this right here, what does it look like? Just think about how the data looks and just be like, okay, this bulldozer sold for $100,000. It was sold 1.04 years ago. It was made in 1994. What was it it was used for 32,000 miles or usage hours. The blade has a width of 16. The tire has a width of 23.5. We can even look at the data set a little bit more in depth by going here and reading about it and finding out these values and what they mean. But what does this look like when you look at data right here? It looks a lot like something we've probably used before. Should just think, okay, this looks a lot just like a simple program from Microsoft. I always tell people to think about, you're just working with a what right here? It's just different names of variables. There's the variable names right here. Here's the name of the data frame. So that's just the name of your Excel worksheet. And these are the vectors inside of here, or the column names. So that's just the name of a variable. So it's just like Excel. It's just like Jump. We just have right here just a data table. Here's the different rows. Here's the names of the variables. Here's the different rows. Here's the names of the variables. Here's the name of the data frame, the name of what we're using. It's called bulldozer. And then it has these vectors inside of it, or variables, I should say. They're all called vectors. Vector is just like a univariate line of data. They're sold at auction. We can predict the selling price of a bulldozer with sale price from its usage. So let's try to do that right here. We've read in the data, and now we want to make a scatter plot where we're going to predict the selling price from the usage. So how would we do that? Well, first, we actually have to create a model right here. We'll do this a few different ways looking at this. So I'm going to shrink the fonts down a little bit. And here we go. Let's make a model. The way I like to do this is I like to store into model M a linear model of sale price. And please notice that sale price has a capital P, and we're going to have it explained by usage. Now, this format right here is very important. This format is the formula format with y tilde x comma data equals. So the first part of this equation, I'll write it in a basic form right here, is y tilde x comma data equals, and then the name of your data frame. This won't run, but let's think about what this does. This function right here is the linear model function. The linear model function is going to create a linear model. It's going to do regression. It's going to take a y variable of interest, sale price, and use the x variable to explain why things sell for a certain price. Now we have to add the data frame here because they're inside of a data frame. So because these are inside of a data frame, data equals name of data frame. Maybe later we won't have that issue. If you have questions, please let me know. If something's not working or you want an elaboration on something, say, hey, can you explain this more? What does this mean? And I'll go into greater detail. So this is storing into M this linear model. So if you notice, we have now created the object M, which is a kind of complex thing. It's a list. It's got a whole bunch of things inside of it, like the coefficients, the residuals, the errors, the effects, the ranks, the fitted, the sign, all these different things are here for us. We are going to use this object to actually plot it. Now, this is the easy way. The easy way to plot models is with visualize model. Let me point something out and make sure people are doing this. Who knows in the chat how many letters? Alyssa, good to see you here. Alyssa, do you know how many letters you have to type before that autocomplete kicks in? Anytime you're typing something, use autocomplete to your advantage because it'll capitalize, it'll spell things correctly. And how many letters do we have to type in for that autocomplete to kick in? And then we can just hit enter. Once we have this right here, once again, don't try to type the whole thing. It's not worth it. You'll make a typo. Nice job, Alyssa, right there. Another 100 points. We typed those 3 letters right there. Angeli, great job too. Another 50 points on top of that. So we type 3 letters, then we just hit enter, or you can select which one you want. So once you hit enter, then put in the name of your model, and you can visualize the model. This plot is pretty interesting the way it works. It'll actually change the size of the window, or that little, what is that called, location or key of sorts, depending on the size of the window. Now, it wants us to use the plot, so let's use it. The plot uses a very similar format. And let's go ahead and plot this. Okay, so plot is going to be, unfortunately, it uses x comma y, x comma y comma data equals. It might work with formula format. Oh, it doesn't like that. I don't use plot nearly as much. Same thing. Tomato, tomato. But we're missing what right now? What are we missing on this? What are we missing on this plot that would be pretty important to use for regression? We don't have something, we just have a plot, but here's a regression plot. Much better. It's got confidence and prediction intervals. We're missing something. We could probably use to put this on there. Oh, so I click it, and then I hit Command or Control C. Thank you, Payne, for asking that. 50 points right there. When I highlight code, I'll just hit like Control C. And then I'll hit Control V to copy it. So I'll use a lot of Control C, Control V. If you want to like remove something, you can hit Control or Command X. Anytime you hear me say Control, that's Control Z to undo. A lot of good, the whole Control Z, Control X, Control C, Control V are very powerful. Copy, paste, undo, cut, all those things are really great to practice. You just get faster with how you can manipulate things. Payne, so thank you for asking that. You're welcome. Yep, just you can double click something to highlight it or triple click it to highlight a whole line. So you might see me triple click a line and then I can paste lines like this. So a lot of times if I have a line I want to repeat, I think that's where we want to be. So if I want to repeat this line right here, I might just do this and then I can repeat the line pretty quickly. So it's just little things like that that make you faster with coding. We want to add the line to this. So I'm going to go AB line. It's just like A to B line. And we're going to add in here the M, and there's the line, but it's hard to see. So we're going to add a second argument to this, and the second argument will be col equals red. This is all just unnecessary. We can add a line width, LW, and these are just arguments, and now it's thicker. It's all just to make it look like this. Cool. Once again, these are 2 separate lines of code right here. One is doing the plot. Always try to go through and understand what it's doing. Okay, we're plotting y, comma, y tilde x from a data frame, and then we're adding the regression line. That's what AB stands for. And then these are additional arguments to set a color for it, and an additional argument to set the line width. Line width is just going to control how wide is that line. That's what line width does. So neat. Just add line. You can add just the black line if you want, though. Black line, or you can add the colors. You can choose your favorite color. Go ahead and go purple. That's purple line. So code fitting and naming the regression model. Well, we already did that because I like to do that. Code adding the regression line. So we've done this right here. Here's the fitting of the regression model. Very important. Who knows what LM stands for? It's got something to do with this. The M right here stands for model. Is there anything change out the comment colors? Oh, like these green ones right here? Yeah, I'll show that next. So change our comment colors? I'll show that next, Michaelos. Great question. Linear model. Good. Ooh, that's what I was going to suggest. You can change the theme, which will change it, but I don't know another way to just change the comment color. I could look into that. Great answers right there, everyone. Linear model. And thank you, everyone, for being here. I'm throwing another 100 points on top of that. Sometimes people show up, sometimes they don't. But either way, people are using these videos, which is what I like. So thank you for watching, if you're watching later. This is the linear model, LM. If you ever see GLM, that stands for Generalized Linear Model. It's a very similar thing. We will use that code later in class. GLM stands for the Generalized Linear Model. There's more versions of the GLM. The LM is only for quantitative, and the GLM is more of a general form. So we will use GLMs later on for generalized linear models. It's a much broader sense of what we can do with that. You're welcome, Mikolos, anytime. So Mikolos, hopefully I'm pronouncing things correctly. It's always my goal too. We're gonna put this helps me tag the videos. So this is where I just do a tiny bit of a break right here. And thank you everyone for being here. So then we're gonna start with the second question here. And so I think we got everything plotted. Let's see right. Oh, it's asking questions. Oh, I should answer them. How's the trajectory look? What do you think? Help me out here. How's that trajectory look? Does that trajectory look mostly linear? And the vertical scatter is about the same? Hard to tell. It's right. Hard to tell after 20,000. So linear regression should be appropriate. Yeah, this is basically just saying. Looks mostly linear. Looks to be a lack of scatter. Who knows the word for we see the plot changing, like the plot is getting thinner throughout here. I always like to go through and start drawing on these. So be like Brian, be like Brian, BLB. And go, yeah, I don't know. It's getting a little bit thinner right there. So I'm thinking we might have an issue with what right here. We were literally talking about this today in time series. I think we ended on it. This is the end of time series right here, pointing out the same issue and pointing out outliers. So these concepts you're learning right now are used in all the courses. This is an issue with what right here? Stat 2.1 calls it plot doesn't thicken. Peyton's got the points right there with some heteroskedasticity. That is changing thickness, heteroskedasticity. Plot is not of even thickness throughout. Not the best. We don't like that. That's not good. Might violate a condition. So here we are on question 2. The value of the slope, its standard error, p-value, and the confidence prediction intervals are reliable only when the model is a reasonable reflection of reality. We're to one of my favorite parts right now. We're going to do the check regression. Who knows the complicated code right here to do a check regression? Since we have our model object M, since we have our model object M, what is the complicated code for doing a check regression on our model? This is where coding is just like, yes, just nice and easy. Nothing too crazy going on right here. Take a moment, just put it in your brain and be like, check regression only takes this argument. There's some additional things we can change about it, but we'll just focus in on just doing this. Let's try typing 3 letters. CHE. Looks pretty good. I got a bunch of stuff, though, because I got a bunch of packages loaded in. If you notice, we have check regression. Nice job, Caitlin. Another 50 points. Excellent work, Caitlin. It's just going to take the model object M and then do a check regression on it. And so what is a check regression? Well, it's checking our regression to see if it's a reasonable reflection of reality. Very important to know that when we do a check regression, we're asking, is this a regression a good idea? Now, this is where confusion happens. Do I still have the notes open from today? Oh, I might have closed it. Yes, I still have the notes open from today. So let's go over to our notes from today and read through a little bit. What is our starting null hypothesis? Oops, there's the right side. It's good. What is our starting null hypothesis when we check a model? If we are checking a model, what do we start out believing about any assumption to begin with? And this is where people get confused. Any assumption we have to begin with when we start out is assumed to be what? This is a generic way of thinking about it. Statisticians are going to be mad if I say this, but whatever. We're business analytics. So what are we generally going to assume about any condition we have right here? Whether it be linearity, normality, or equal spread, anything we have right here, would it be assumed to be what? Any condition we have is assumed to be what? Like we look at the condition, we say, I assume that's this. What will we assume just with any condition we look at? To start out. Just starting out, null hypothesis, that's what the null means. We will just assume this at the start. It'll be our base assumption that it is what? I promise it's not a trick question. The starting assumption for all these conditions is that the condition, and by good right there, I mean it's met. It's good right there, Payne, you're right. The starting assumption is that any condition's good. We just say, it's good until we have evidence it's bad. And what do we mean by evidence? Low p-value. Low p-values are evidence for the alternative, evidence it's bad. So let's be careful. I want you to look at this regression right here, which we did in class. And with this regression, I want you to tell me first, how many conditions are there? Be careful. These are where the mistakes are made. How many conditions are there? How many conditions are there? This is a good drill. You might have done this during class, but you should be like, okay, there's always this many conditions. Multiple world will change things a little bit. So there's always this many conditions. This many things we'll check. How many things will we check? Now, it might be tricked, and I'll explain why. But how many things are there to check? They should list them. You should be like, okay, there's linearity. There's equal spread. Great job, Peyton, right there. Great job. There's linearity. There's equal spread, and there's normality. Now, the reason that there's two p-values here is because the p-value of the x is the same as with the model. That's because we're in the simple world. So in the multiple world, there'll be p-values for each of the x's and each of the models. Great job, Caitlin, there too. Some more points in the chat. So in the simple world, the p-value of the x is always the p-value of the model for linearity. And we check the x's if there's multiple x's. Multiple world will change things just a little bit. So now when you look at this, is this good or bad? I want you to answer this. You can read the slide to help. But is this good or bad? These p-values are all pretty high. So is that good or bad? Are we happy or sad right here? What do you think? These p-values are pretty high. They're not below 0.05. Just let that null fly. If you remember what the null was, it'd be that all of these conditions are good. You can be like, the null is that linearity is good. The null is that equal spread is good. The null is that normality of residuals is good. And the alternative would be we have evidence they're bad. Like when you reject the null, you have evidence for the alternative. So what would we think right here? All these p-values are high. Don't reject the null. That's the statistical way of putting it. But you just say to someone, yeah, my model is what? Looks like my model is pretty what? Remember, this is where people make mistakes. I caught a lot of people in class with this today. Because you're like, wait, low is good. No, it depends on what you're assuming. We are assuming our model's good and looking for evidence it's bad. So in all of these, we do not reject the null. So Peyton, you're right. This is all very good right here. So all of this is very good. And so we don't want evidence. So actually, there isn't evidence that they are bad. So the statistical way of saying this would be, we did not find evidence that the model has issues. Does that make sense? We assumed the model is good, and we failed to find evidence the model has issues. That's very statistically to say, or we could just say the model looks good. No one's going to really ask us about the p-values, but our model did not have violations of conditions to show evidence of a problem. But some models will, especially models that look like this right here. We'll go to this model. This is a review from notes from class. We'll just delete everything for right now. But if you look at this model over here, this model is absolutely horrible. And as one would expect, if you look at it, the normality of residuals has major problems. The equal spread is ridiculous. The linearity might be okay. We do not want evidence for the alternative, correct? Because the alternative is that it's bad, that we fail the condition. So the alternative, we don't want evidence for. So tell me, are you happy or sad right here? Are you happy or sad? Because you want to use your model. You made a model to use it. You made this linear model that looks something like this, and then the data goes something like this around it here. Pretty sad. And this is definitely where we're going to see a failure on the equal spread, because no way, no how does that have equal spread. So that's going to show up in the residual plot over here where you see the unequal spread. Now, here's another mistake people make. When you look at these plots right here, which plot plot 1, 2, or 3 is where we will check equal spread. Plot 1, 2, or 3. Sorry, Angela, here's some points to cheer up. Plot 1, 2, or 3 is where we'll check equal spread. Plot 1, 2, or 3 is where we will look to see, is there equal spread? Which plot will we look at? Plot 1, 2, or 3 to see if there's equal spread. Like, is the equal spread good or bad? I should look at which one of these plots. Don't worry, Peyton. Plot 1. Plot 1 for equal spread. Great job, Caitlin, right there. Some more points for everybody. Great job. Don't worry if you get things wrong. We get things wrong now to get them right on the test. Which plot will we look at to look at the normality of the residuals? Which plot will we look at to look at the normality of the residuals? Which plot will we look at to look at the normality of the residuals? Plot 1, 2, or 3 for normality. Hunter, excellent work. Hunter swooping in there. The QQ plot for normality of residuals. And so that's where we look at for normality of residuals. Which plot will we look at for the linearity of our model? Which plot will we look at for the linearity of our model? Plot 1, 2, or 3 for the linearity of our model. Which plot will have us look for the linearity to see if the line is a good approximation, goes through the center of the data? Good practice review right here. Then we're going to look at our model for the other thing. Plot 1, Caitlin, we're the 100 points right there, crushing it. Great job. Plot 1, that is the line right there. So a lot of people think, wait a minute, why am I not looking at the histogram? Don't look at histograms. They're a bad idea. Don't look at that. That's bad. So that is the linearity right there. And so we're looking to see if it's linear. Does the line go through the center of the data? And overall, it looks like the biggest issues here are probably with the normality of residuals and the equal spread. So I'd say, even though we fail all the conditions, I'm going to say the big problems here come from normality of residuals and equal spread. So make sure to practice up, and we're going to look at our plots. So the first step when we have these plots, we'll go through each step. Step 1, look at p-values. How many of the 3 tests do we fail right now? Step 1 is to look at p-values, and are they below 0.05? How many of those tests do we fail? Remember, there's only 3 tests. We have linearity of the model. All 3. Bad, bad, bad. Boston. Step 2, which is listed down here for you, is going to be, is our sample size large enough to continue? 25 or larger. So it was 25 or larger. Can we continue? Is our sample size 25 or larger? Sample size. Oh, that's N. Is our sample size? It is. There's the sample size. And this isn't really like a pass thing. It's like a continue. It's like you get a second chance. Second chance, I don't know about it. We'll find out in a moment. So what should we look at now? It's behind me. I'll have to go away. Step number 3. So we're going to examine the diagnostic plots, and probably a pretty large concern to me is going to be what? What do you think a pretty kind of concern to me is going to be? Where do I see my concerns at? What would you be most concerned about with this, and where? I've got like moderate concerns on certain things. What concerns do you have and where? There's only one I'm not concerned about. I'm like, it's whatever. The spread, the spread, I do agree. It might actually, it's one of the points I lost in graduate school. Dr. Me hopefully he remembers this. But when you have less data will generally have less variation. So the spread is of concern, but the fact that there's less data would indicate probably less spread. I don't think the line's an issue. Does the line maybe slice through this pretty well? Does the line cut through the center of that? The line is the only one I would not be concerned about. But I'd also be concerned about the what over here. What issue am I pointing to over here? It says it below here. Yeah, exactly, Caitlin. Excellent work. The normality has problems at the end of the QQ plot. So yeah, the normality looks to have some pretty bad issues. Equal spread might be a symptom of lack of data. Great job, Mikolos there. Extra points on top of this. So I would say, like, sometimes I ask to give people grades on these. I'd give this a D. I'd give this a C plus. And then the linearity, I'd give like a B. It's doing okay. I'll give it a B plus. I'm not super happy with it. I'm not super sad. So I'm trying to tell you most of the issues I think come from the normality of residuals. Equal spread could be something, and then the linearity is kind of okay. I don't know, not super happy with it, but yeah. I mean, if I got all B pluses in high school, I'd be super excited. My parents would have been like, what the heck? Who are you? So we've texted it. We checked it. The textual output gives the results of the test right here. How many of the tests are passed or failed? Failure. 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 We already know that our model is wrong. Important note to have right here. And we've kind of commented on these already. Famous quote. You should know. All models are wrong. Some are useful. If I have a clock in my room that's exactly 12 hours off, do you think that clock would... It's like, I'm telling you, perfectly, like to the atomic clock, it's exactly 12 hours off. That's as far off as a clock can be from any sort of clock. It's 100% wrong all the time. But do you think that clock would be very useful? Why or why not? It's a very, very, very wrong clock. It is perfectly wrong as perfectly wrong could be. So when it's 11:59 p.m., it says 11:59 a.m. I got to throw that clock out, right? And I'm saying it's perfect. Like, literally, I could watch the atomic clock and it'd be so synced with it, it'd be scary. You'd be like, how is the clock that perfect? How can it tell time that perfectly? But I say, I got to toss it out because it says AM instead of PM. Just flip it. It's so useful, yet it's so wrong. With this right here, we know our models are wrong. All models are wrong. No model is the right model because we're trying to use math to describe the world around us. And it's like, you can't do that. You can't use math to describe the world around you. But guess what? Sometimes we get a model. It's kind of useful. This model got a lot of wrong. Might have some use. So we acknowledge that our models will be wrong, just like that clock. But some of them might actually come into some great use to make decisions. And that's when a model is useful, if we can actually use it. So there's the comments. We went through these comments a moment ago. I'll go through them real quickly. Linearity actually looks to be okay. Its p-value is the least worst. Like, you want a high p-value. And I don't really see an issue with this line not going through the center of the data. The equal spread looks to have some moderate issues of concern, maybe due to lack of data. And last but not least, we have the normality of the residuals behind me right here. And this is your perfect normal line, this line right here. Just to show this off, if you were to have a QQ plot for normality and you had data that was normal, it would follow the red line. If you have data that is not normal, the less normal it is, the less it'll follow the red line. So once again, normal data follows the red line. These are random normal points. Non-normal data will not follow the line. So what we're trying to examine by looking at this is we're trying to ask, how far away is our data from that red line? And that's bad, and that's bad. And so we don't want those. So I'm saying that's probably the worst issue right there. That is not good. Okay. Next question. How is everyone doing? What questions are there? We're pretty far into this. I like this chapter a lot. I like this kind of stuff. I think once you get the hang of it, you're like, okay, check the regression, look at this, look at this. It's very formulaic in what we're doing, or very structured, I should say. So it's like, okay, I'll check my regression and see if it meets these three conditions. I'll see if the p-values are low. That's a problem. If the p-values are low, I'll look at the sample size. If the sample size is large enough, I'll continue. And if we continue on, I'll look at the diagnostic plots to see if we can actually save this regression and use it. It needs to be a reasonable reflection of reality. Reasonable, has to be okay. Doesn't have to be perfect. Continuing on, next question. In my opinion, it takes years to build up the intuition. None of the violations look to be severe enough to invalidate the model. Look at the regression lines along the confidence prediction intervals. Have the legend appear in the top right. On the activity due tomorrow, it asks for predict the... Yeah, we'll look at that here in a moment. Great questions, Peyton. We'll be doing that here soon. I can do exactly that. So the loc right here, I think, how many should be outside? Yeah. So here we are with the visualized model. When you visualize the model, it'll put it in the top left. The additional argument loc moves the location of it so you can kind of see better. Oh, I didn't close it. Ooh, I didn't do something. Oh, I didn't close the parentheses. If you ever get this plus down here, this is a common error. It's asking for more code. One way to fix it is to just type something random. Oh, we're stuck. We're done. You can hit escape. There we go. Sometimes you can break the code if you type something extra. Oh, I know why I was doing that. Because I was still in the string. If you look what happened here is the string didn't end, so I could end the string when I'm still in the string because it's doing that. There we go. Now you can break it. You can either break it or just hit escape and get out of it. Happens a lot. Very common error. And then I've had students come to me and say, I've been running things for an hour and nothing runs. Just because you've been appending code. That's the appending code right there. So going to the top right there just moves it out of the way a little bit. Another thing I like to do with this if I don't want to see it is I just move it to a random spot and it goes away. That just moves the location of the legend right there so you don't have to see it. Important that we know what these things are though, and this is getting towards Peyton's question. We've got a very tight interval right here and a very wide interval. So what is this tight interval and what is this wide interval and what's the point of this? Legend will probably help us out with this. What's the very tight interval and what's the very wide interval and what's the point of these things? A confidence interval and a prediction interval? What? What are these things? Help me out. What's going on? What's a confidence interval? Prediction interval? What? I am stuck in this void. Anybody? I'm just lost here. What is a confidence interval and a prediction interval? I don't know. These are two separate intervals. Obviously, you can see it. So they do two separate things. More obvious. A confidence interval is the tighter one, and the confidence interval is for the mean of all points. I wish I could. The confidence interval is for the mean of all points. When you do the mean, you have more data. All I can do is, waiter. That's all I know. Great movie, SpongeBob movie. And then the prediction interval is for an individual. So the prediction interval here is for one bulldozer, and then the confidence interval here is for all bulldozers of that usage. So if I make a prediction interval, I will get the wider one, which has more variation, which it probably encompasses 95% of the points because it's for individual points. An individual bulldozer with 10,000 usage would have a prediction interval. All bulldozers would be expected to have a price on average within the confidence interval. So the confidence interval is when we make predictions for all bulldozers of usage 10,000. But the prediction interval would be for when we make prediction intervals for an individual bulldozer. I can't make this more clear that this is for, let's draw on it to make it even more clear. Helps to take notes, so I will take notes too. But the key terminology here to know is that the confidence interval is for all, and the prediction interval is for one bulldozer. Hence, the prediction interval is much wider. There is more uncertainty than the confidence interval where you are doing one. I mean, all of them. Steven, I make mistakes. Now, you might say, but wait a minute, this is getting wider. This is due to the equations and how they're written. Please go watch class if you don't know this. This is a lot more theory than I'll get into right now. But the way the equations work right here, we're drawing a little bit more today. The way the equations work is the further you are away from the mean of x, the more uncertainty there is. The more the sample size, the less the uncertainty. The more the variation in the x, which is standard deviation of x, the less the uncertainty, because this is in the denominator of the equation that finds the uncertainty in the intervals. The larger the typical miss, the more the uncertainty, and that's just the spread of the residuals. Pretty good equation to understand, and this equation that builds our prediction, our confidence interval, uncertainty, is the same equation here, but you'll notice it just has one plus, and this is now for an individual for prediction intervals. So they're based on the same sort of logic right here on what we were doing, and there we are. There it is. Obtain, here we go. Obtain a 95% confidence interval. So we are predicting for how many bulldozers right now? One or all? Good review. How many bulldozers are we predicting right now for? One bulldozer or all the bulldozers? A confidence interval. Look at the cheat sheet over there. One or all the bulldozers. If I'm using a confidence interval right now, using my model to make confidence intervals, am I predicting for one or all of them? Am I predicting for one or all of them? Since I'm doing a confidence interval, so remember, look at the graph behind me. Great job, Kaylin, everyone. Great job, another 100 points. Why not? Just go crazy on those points. Now, so all I need to type is confident, right? Right? No. What is this? This is important, but what is this? This is confidence intervals to estimate the what? This is not what we want. This is confidence intervals to estimate what? Important we know what confident gets us. Hey, Connor, good to see you here. Thank you, Connor. These are confidence intervals to estimate what? Oh, that's what confident does. Confident does get me confidence intervals to estimate the true values of my what. So you make sure it writes down what confident does. We were talking about this today in class too. Confident is a code that gets you, if you put your model in it, gets you confidence intervals to estimate what? What are we getting with confident right there? Confident is a code that builds confidence intervals to estimate the true coefficients for your model. And you know what's really interesting? This right here is if you were to take and add to it 0.4, you get that. Because a 95% confidence interval is just plus or minus 2 standard errors most of the time. Pretty close to that. So all I did was add to this 2 standard errors, and I could subtract. Like, what is 0.6 minus 0.4, which is 2 times that? It's right about this right here. What is 80,000 minus 4,000? Well, you can notice right here, these numbers are basically this plus or minus 2 times this. Important stuff to know, just a little extra theory right there to know for the test about how those confidence intervals are built. The code we're looking for, these codes, this is not the code you're looking for right here. The code you're looking for is to build a confidence interval. And to build a confidence interval, you need new data to make predictions on. This builds a data frame, and let's take a look at it. I usually call it the DF for data frame. So now inside of this DF right here, we have our what variable. Type in one letter. Your data frame that you use to make predictions must have your what variable inside of it, or multiples of these if you're using multiple of them. Inside of this is our what variable, not this variable, this variable. To make predictions, you need your what variable inside your data frame. A lot of people have trouble with this, especially on the take-homes, because they forget when you make predictions, you will build a data frame that has inside of it your what variable. It'll always be the exact, do not make typos, the exact name of the what variable. And this is a vector of values we are using for it. One letter, just one letter, not this one letter. Go back to algebra or go back to whatever class you learned these in. Not this letter, but this letter. So what variable, it'll always be your what variables. Great job, Peyton, right there. Your X variables, you got it with some points right there. It'll be your X. Mikolos, excellent work, Mikolos. Throw us some extra points right there. Yep, this is how we practice. Okay, so the data frame function builds a data frame. We need to put the name of our X variable in here, and then this is just a vector of values it's taking on. And you can see it. Well, and watch this. If I go here and I say I want another variable, Brian, then the variable Brian is going to take on values this, and look at my data frame. Is it making sense what this does right here? This gets turned into the first column. This, which is the second variable, gets turned into the second column. Just try to walk through what is the code doing. It's building a data frame. We're saying this is the name of the first variable, and these are the values for it. This is the name of the second variable. These are the values for it. And then we're storing the object into what I call df, shortest way for me to write data frame right there. So the data frame function builds a data frame. We use it to put our X variables in it. We're not going to have a Brian variable. Sorry, Brian. And we are going to have the X variable usage, and then we're going to have no other X variables. So let's actually build it. This is very important right here, because when we use the actual function we want, predict needs a model to make predictions on. This just predicted for all the values inside the model. Can you graph it with 2 columns? Maybe. I think, did I do that? Good question. Payne, to expand upon that, I might have or I might not have. And now we want to go here and go new data. Ooh, don't do that. Don't let, for once, autocomplete's not going to help you. So what are these? What did I just get? It's important we always ask ourselves, what did we just get by running this code? I say predict using my model and use new data of this data frame. So what's this? What's this? What are any of these? Predict using my model on the new data in the data frame. How are these connected? Oh, if I I could try. What is 79,500? Could find it the hard way. 79,500 is the expected price of what? 79,500 is the expected price of a new bulldozer. No usage. Remember the next one we saw just a moment ago? We saw this. Well, that second one is the second value here, which is the expected price of a bulldozer with 10,000 usage. It's probably doing more decimals in the background that we don't see. It better be. And the last one is the expected selling price of a bulldozer. I think it's carrying some extra decimals we're not seeing. Reason being is when we look at the summary right here, it's going to round the numbers. So what I could do, I'm just going to do one last thing because I don't like when things come out different. Options digits equals 20. It's time for a little hacker man right here. Where's my hacker man at? Wrong button. Oh my gosh. Back to the main screen. We're making this happen right here. We're making the numbers turn out exact. Okay. That's some numbers right there. So here's our model. Down to like ridiculous decimal place accuracy. We're not going to let things turn out different on us. Not today. Not today, R. Oh, look at that. There's my prediction. Now the content's going to, or now the prediction. There we go. Yes, look at that decimal place accuracy. Beautiful. Next, we get our other prediction right here, confirming that the issue was not carrying significant digits. So now let's go back to not carrying significant digits. This sets the global options. Little hacker man to the rescue. Output looks good again. Heck yeah, we're going to hack the mainframe right there. If you change your global digits, you can get ridiculous output. Watch out. Be very careful if you change the global digits. You'll get weird output. But once again, I just wanted to confirm that R is actually carrying more digits in the background, doing the final rounding at the end. So those differences we were seeing by doing it by hand. And this is once again why we don't do things by hand. We let it do the work for us. So when I'm doing this right here, what is it doing? It's solving the regression equation. Does that make sense what it's doing for me? It's carrying all those digits. We don't have to do that. It'll do all the work for us and plug 30,000 in because 30,000 is a value of X. We said, can you make predictions for me for 0, 10,000, and 30,000? It said, sure, why not? Here's your predictions. And we said, oh man, you did all the hard work. I would have had to do that by hand right here, and I get the same answer. Now I get the same answers, and I like that. but we're not getting confidence intervals yet. For this, we need an additional what? I'll pause right here. I'm putting a comma. So I need an additional what? What do I need? What am I adding by doing interval equals this right here? I've added an additional what now? So I've added, by doing a comma, you say, well, we need to put an additional this in. Add in an additional what? Just an additional set of instructions. Make predictions using Model M, predict on my new data, and give me intervals that are based on confidence intervals for the mean. That last set of instructions, there were 3 of these in what I told you. The function of predict is using this, and this. So these are 3 separate arguments. Arguments are just like different things we're telling it to do. So now we get the confidence intervals. And so now that first brand new bulldozer, I would expect, and that's the red line right here, to be selling for $79,500, which is the intercept. I would be 95% confident the average for all bulldozers that are brand new is contained in the range. And this is like the average of all bulldozers. So it's the expected average price of all bulldozers that are brand new is somewhere in this interval here to here. Next, we could talk about the other ones. So maybe some answers to the other questions down here. But we can easily change this code to do it for an individual bulldozer. This is an individual bulldozer. And what's immediately going to happen to my bulldozer interval right here when I do it for one bulldozer, not the average of all bulldozers? When I do it for one bulldozer, which is a prediction interval, the prediction interval will always be water. Like you can see it. All bulldozers, one singular bulldozer. All bulldozers, one bulldozer. Prediction intervals for an individual bulldozer's selling price. Like, how much will that individual brand new bulldozer sell for? It's going to be a little bit odd. It'll be much, 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 much wider. And look at this. A brand new bulldozer probably ranges, a singular one, like one brand new bulldozer might be somewhere between about $12,811 to about $146,000. That's an individual. I'm 95% confident the price of one bulldozer is probably in that range. What's even weirder is we get some negative numbers up here for a bulldozer with 30,000 usage. How do I know that this one's for 30,000 usage? Remember, we're predicting for 3 bulldozers. One was 0, 10, and 30,000. But we could always extrapolate. Why not? Let's go over here and predict for a bulldozer with 100,000. My model was not supposed to do this. But now when I make these intervals, I'll have a 4th one in here. Remember, first prediction, second, third, 4th. So now a bulldozer with 100,000 units of usage would probably sell somewhere between them paying you $58,000 to you paying them about $100,000. This is not good. This is an extrapolation of the model, and it gets even wackier and less reliable if you go out crazier. The model doesn't care. It's going to do the math for you, and now everything's negative on this last one. Once again, it goes in the order by which you give them, predicting for each one of these. This is the predicted value, and this is the interval predicting for one individual bulldozer because we're using the prediction interval right here. Got some stuff right here. Oh my gosh, so much text. I think it's got it. This is just explanation right here. And I think now we're going to start doing some transformations. Yeah, let's hear it. Make a scatter plot to visualize the relation you're made. Check questions, see if the residuals. Oh yeah, okay, we'll do that right here real quick. Hop back in here. And thank you, everybody. We got a little more time right here. Finish up. We'll do some check regression or find transformations on this. So let's go ahead and look at this and make a scatter plot to visualize, and you're made. Okay. So what I would do is I would grab what I've already done and check it out. We're just going to go down here and that's not where we're at. I want to go to year made. All we're going to do is going to go to year made, capital M. And we got it. It looks like. Oh, do you see it? What condition is obviously going to be failed right here? There is a strong failure of a condition right here. Very strong, very apparent condition right here that's like, no, no, no. This is not good. So is this graphic. We'll fix it though. what condition. You can see it especially down here, up here. Might even be better in this graphic right here. There's something I can do. Maybe you can see it a little better now. There might be some normality of residual pain. Good answer right there. Do you see it a little better now? If I fit these polynomial models, something we'll be doing later on, if I fit these polynomial models, they go a little bit better through the data. You can see here a little bit better R squares with the polynomial datas. So maybe the problem is with the what? Maybe a first order polynomial would be raising something to the first power. So what do you think I'm trying to point out to you right here with this graphic is like maybe there's an issue with the what of the data right now. Because it looks to have like this bend through it. So maybe this right here is not the best of ideas. So the problem looks to be maybe there's a problem with linearity. You don't have to know how to make this plot yet, but this is just the choose order function. We will do it later on. But I think it helps show that there's a little bit of a bend. It's fitting models that can bend, and the bend is useful. Great job right there, Peyton. I would say, yeah, there looks to be some linearity issues. Choose order is a really cool function. So let's see. So yeah, check the regression. Check regression. One thing I'd like to say also is you can actually make typos and it'll actually search through. So it's pretty smart. If you do check regression, it'll autocorrect. So autocorrect is very good, very awesome. And you can really see the bend. How many conditions do we pass? Real quick, easy in the chat, real quick practice. How many conditions do we pass? And I'm actually shocked we pass it. Because looking at it visually, I half think there's an issue. No, maybe it's just more of that linearity issue. How many conditions do we pass? Which actually, visually, we might pass another. We only pass one. We only pass the equal spread. Apparently, this has equal spread. The linearity is horrible. The line does not cut through the data, especially here at the start. You can see it looks like the data is flowing downward. You don't want all these points above the line. That's horrible. The model has a nonlinear trend to it, something nonlinear, and you can see that right here, and the bend is apparent if I fit polynomial models. The normality is actually not that bad, and the equal spread we pass. So really, the only big problem here is the linearity. So when we get down to this, we go, well, this is mainly like, sure, that's another check regression right there. Another check regression out of the way. Kind of a quicker check regression than we did earlier. So with number 5 right here, we're going to run the find transformation. And shocker.
Wow.
Find transformations is going to find transformations for us. What do I mean? Well, it's going to look for possible ways to transform this to make the model better. Here's our model with no transformation. Uh-oh. Here's our model with the best transformation. Doesn't look that different to me. Sometimes you don't win. It says we should raise y to the 0.5 power. We should raise x to the 1.75 power. So let's take a look. If we go here and go to the bulldozer data, and our y value was sale price, it says take sale price and raise it to the 0.5 power. So there's sale price raised to the 0.5. So let's call this y transformed. Now we're going to do the same thing, but we're going to make an x transformed. Copy paste. Good stuff right there. And the x variable, yeah, year made. And we're going to raise x to the 1.75 power. Oh, overwrote my y transform. Watch out. Now, these values right here, when I write my code to make the model, do not need to be in a data frame. You might be wondering why my x trans and my y trans right here don't need to be in a data frame, and I am putting it the wrong way. The reason is because these vectors are not inside of a data frame. Remember, if we use data frame, it's because they're inside of a data frame, but right now the x trans and the y trans variable are just floating out here in the global environment. So when I make this model right here, I will not put a data equals. That's a graphics error, so we're all right. And so now, let's go to visualize model, and doesn't look much better to me. Not good. Still not great. Let's go to check regression. It's about to be a sad day. Check, oh, because I didn't catch that. Oh, I overwrote my M. Okay, that works. Let me point this out. Usually I call this M trans, and for my transform model, and I'm making so many typos. it actually, in my opinion, made things worse. Sometimes, and we like to do this every once in a while, sometimes transformations are not the answer. Sometimes you transform and you say, you know, that was not a good idea. It doesn't fix everything. And this one definitely didn't, because the p-values got worse. Going back and looking at our previous model, I'm going to run all code above, so you can see a bunch of things appear over here. Our previous model had an R squared of, is this the same? It's year made, good. Had an R squared of 54.3%. Not bad. 54.3% of the variation in the sale price is explained by the year made. Kind of makes sense, you know, how old a bulldozer is. Our transformed model explains 55.26. Very important note right here. I have a question on number 2 on the quiz. If you have, yeah, let's do that. We'll do that. You bet, Kaylin. Thanks for asking. So quick question right here. The differences between these right here, the multiple R squareds, it increased by about 1%, a little bit less than. So this would be a change in the what significance of the model. So I'm saying my model first explains 54.3% of the variation, and my model now explains 55.26% of the variation in the price of a bulldozer when we use year made. So this is a change in the what significance of the model. R squared is always the this significance. The p-value, this model is super significant. Any way we cut it, the p-value here is ridiculously significant, ridiculously significant. Everything is good on statistical significance. Conditions are not the best. But the change in the R squared means it's a little more this, but it's so little. It's too little for me. I don't like it. The change in the R squared right here is an increase in the practical significance, like the, oh, this model does something cool. And it really doesn't do much cooler stuff. It's 54% of the way driving you to New York, or 55. It really doesn't help me out that much. So overall, I'd say this model didn't gain much from getting a transformation. So should we transform it? I'd say no. I'm going to say no right here. Oh, transformations don't always work. Who'd have thought? So fitting the suggested model right here, fit a linear model, then run the regression. Does it appear? So yeah. So we always fit the suggested model. Check it out. Yep. I guess got it. I think we just did it because we just did this right here. But rather function quantities like find. Yep. And we just did. So we just actually did 6 and 7. Let's take a look at Caitlin's question right here. We'll hop to the main screen. Let's do that number 2. Question number 2. Let's see right here. What's this? Storm in Knoxville. Preview. Question number 2. Consider a linear regression model to predict the selling price of a bulldozer from its usage. What is the predicted sales price for a bulldozer with a usage of 10,000? So help me out here. I'm not going to put the answer in the chat, but I want you to walk through this with me. What first must you do? Is this... Let me ask Kaylin again real quick. So you're wondering about this one right here, right? So I'm not going to put the answer out here, though. So it says, what is the predicted sales price for a bulldozer? For a bulldozer. What is the upper limit of 95? Prediction interval, yep. So one thing to do to help with this is to limit output. I'm not going to say the answer, but I'll kind of point to it. We're doing 10,000, right? How many bulldozers will I predict for now? How many bulldozers will I predict for? I might just do this. How many bulldozers will I predict for now? So if I make this data set right here and I use it to make predictions, how many bulldozers? We'll predict for 1. So here's the thing though. Do I need prediction intervals? Do right now it says, what is the predicted sales price for a bulldozer? So do I need prediction intervals right now? It just says, what does it predict? Do I need prediction intervals? Because it just says, what is the sales price? So we don't have a boundary on it. We're not saying like for an individual bulldozer. It does say a bulldozer, but we don't need those prediction intervals. So let's go here and go to new data equals, and I like to call it df for data frame. Ooh. Oh, because I have a different model made. 2 seconds. I had changed my x's in my model. So down lower, we were doing different stuff. So you're saying, oh, I think check your rounding. Check your rounding. I think it's a rounding issue. Because it says round to the nearest dollar, right? Wonder why. How do you do prediction intervals? You must add in an additional what? To do prediction intervals, you must add in an additional what? To do prediction intervals, you must add in an additional what? To get prediction intervals, you must add in an additional what? If you send me a screenshot, Kaylin, it's weird because your answer is close, it looks like, but I wonder why it's rounding it that way. Oh, you might have done it. I think I know what happened. And then it has to be in quotes. Has to be in quotes. If you don't put this in quotes right here, I think it doesn't give you the output. It's mad. It just gets mad and breaks. Caitlin, did you do it the way I did it by doing the summary? You might have done it this way, which I would not suggest because it doesn't carry enough significant digits. Actually worked? Why didn't it work last time? I don't know why. Is it when it doesn't carry that digit? Oh, that might have done it. You did that in the predict function came out with that? Well, double check, see if it's coming out the right answer now. Yeah, the predict function should. Wonder why it wouldn't. Should carry enough decimals in the background. The answer is just can't say if it's right or not, but yeah. Like I wonder why. It should do it. If you want to send me what happened or send me your RMD, I can take a look. But I think it's got it. I think do people feel like they understand do you feel like you understand this a little bit better now? Yes, great job, Kaylin. Excellent work. Extra 100 points. What do people think? I'm hoping these activities get a lot of watches, which I'm very proud of. Proud of everyone. If you're watching it now, if you're watching it later, I appreciate it. Try to do them every week right here. Long day on Tuesday, Thursday, but you know what? We're here. We got this. And hopefully this has helped you better understand the code you're doing, reading the output, and like why we do these things. It's not about just punching things into the computer. It's like, oh, let me make predictions. Let me understand what's going on right here. Let me make a model. So you're welcome, Peyton. I appreciate everyone being here. It's easier doing these when there's people here in the chat like talking to me. So you're welcome, Caitlin and Peyton. Thank you so much. We'll be back. We'll have more Puppet Shark. You bet. We'll end with some Morty right here. Morty is going to say bye to everybody. Bye for now. Bye.